Hello everyone, welcome to 812 Day 2. We're going to continue our discussion of double and triple roots today. We're going to kind of also review some of the stuff that we've done in the first lesson from 811. So we're going to kind of go over factoring a little bit today, and then we're going to get back into that discussion about leading coefficient, degrees, and behaviors, double roots and triple roots, and all of this new stuff that we have learned so far. So let's just get right into it. We've got factoring up first. Okay, so factoring is going to become a big deal. We're going to see some factoring on the first quiz, and as we move into the second half of the chapter, that factoring is going to become a big deal again as we start learning algebraic approaches to taking higher order polynomials and breaking them down into their factored form. All right, so let's take a look here. We've got a polynomial. It's a second degree polynomial. We call that a quadratic. Okay, and our goal is to factor this thing. We want to get it into its factored form, so it looks like this, where we have it's two factors, right? It's a second degree polynomial, so we're going to have two factors here, and then we eventually want to find the roots of this polynomial. All right, and we know how to do this. We've known how to do this since Algebra 1. We're going to take our polynomial, we're going to use the box and diamond method to factor. All right, so we've got 2x squared. We throw that in the upper left-hand corner here, and then we take the 15, the constant on the end, and we put that in the bottom right-hand corner. Okay, so the other two boxes that are remaining here, these two boxes, they have to add to give us this middle term because it's the only part of the polynomial not represented in the box thus far. So we're going to put that 13x in the bottom of the diamond, because remember, the bottom of the diamond represents what we need to add to. All right, now the top of the diamond represents what we need to multiply to, and we can figure that out by taking the diagonal that we already have filled in and multiplying, right? So 15 times 2x squared is 30x squared. All right, so we need to multiply to 30, we need to add to 13, so we're looking for two numbers that do that. The two numbers that are going to work here are 10 and 3, and we want to make sure we get our x's in there. So we got 10x times 3x, which is 30x squared, and when I do 10x plus 3x, we get the 13x. Okay, so I'm going to go ahead and fill in my other diagonal with those two numbers, 10x and 3x, and then we're going to start working on the outside dimensions here. All right, so since this is a 2x squared, we're going to need a 2x and an x here to go around this smaller rectangle, but we're going to have to put the 2x over here and the x up top. Reason being is because the 2 goes into the 2 and the 10 nice and even, whereas if I were to put the 2 up here, it would go into the 2 but not the 3. Okay, so we want to make sure that there is a common factor of 2 wherever we place that 2x. Okay, so now we're looking at 2x times something gives me 10x, so that means we're going to need a 5 up here. 2x times 5 is 10x, and then down here we're going to need a 3 since x times 3 gives me 3x. All right, now if we look at the sides here, we can see our factors. We've got a 2x plus 3 going down the side of the box here, and we got an x plus 5 going across the top. So now we want to figure out what the roots are. Remember, the roots are the values of x that make either of the factors 0. This one's really easy to see. We know this one is an x plus 5, so if I were to put a negative 5 in here, that would create a 0. So one of our roots is negative 5, and the other one, I might need to do a little bit of work on that one. So if we just take 2x plus 3 and set it equal to 0, we can do a little bit of algebra and just solve this thing. So I can subtract 3 from both sides. We get 2x equals negative 3, then divide by 2. We find that x equals negative 3 halves. That becomes my other root. So there's my two roots. Remember, it is a second degree polynomial, so we had two linear factors, we had two roots, and we found both of those roots using that zero product property. All right. Okay, so now let's get into some of the higher order polynomials, right? Because we're trying to graduate from just quadratics and getting into some more complicated polynomials, higher order, which means they have higher degrees, right? So when we consider the polynomial that we have here, the first question they want to know is, what is the degree of the polynomial? Well, we look through the polynomial. This is in standard form. It's not factored for, so we look for the highest exponent, right? So I see a 7, a 4, a 3. So the 7 is the largest exponent in this polynomial, so the degree of the polynomial is going to be 7. right? This constant term, right, we're looking for a term that's constant, does not have the ability to change, therefore it would not have an x, right, because x is the quantity that has the ability to change. That's why it's called a variable, right? So all of these have an x in it except for the plus 10 here on the end, so our constant term is 10. All right, the leading coefficient, we find the leading coefficient in standard form. It is the coefficient with the term that has the highest exponent. So if we look at terms, right, these are terms here. Anything in between a plus or a minus sign is a term. The highest exponent is this one with the 7, and the coefficient here, or the number in front, is an 8. So that would mean that 8 is the leading coefficient. All right. Now this next question, how many linear factors will this polynomial have? So when we say something is a linear factor, it means it's a factor that has an x in it. So when we go back to the problem that we did before, the quadratic that we factored, we produced 2 linear factors. So we have this parenthesis and this parenthesis. We consider those linear factors because they both have an x raised to the first power in those parentheses. So these are linear factors. And as it turns out, if a polynomial has a degree of 7, we will have 7 linear factors in that polynomial. So the number of linear factors corresponds with the degree of the polynomial. Okay, so let's check out the end behavior. So with the end behavior, we've got to find 2 things. We got to look at the degree and determine whether or not it is even or odd. Since the degree is 7 here, it is odd. Right, so it's got an odd degree, and then we look at the leading coefficient. We really don't care what the leading coefficient is, we just care about whether or not it's positive or negative. So this is a positive 8, so it's an odd positive, and you would need to go back to your notes, take a look at that table that we created, and you would see that an odd positive goes down on the left, up on the right. Okay, so this would be our end behavior, right? If I were looking at the ends of our polynomial on the graph, I can tell you this is what the polynomial is going to do on the ends, right? On the left end and on the right end. All right, let's do another one, but this time we'll start in factored form, right? So we can tell this one is factored because we see the parentheses being multiplied, so we can see the linear factors here, giving away that it is in factored form. Okay, so the degree of the polynomial, we do need to be careful here. What a lot of students will do is they'll just go in here and they'll say, okay, well here's 1, 2, 3, 4, right? And they'll say, well, this is a 4th degree polynomial because I see 4 sets of parentheses with an x in it, so that's 4 linear factors, and we should have a degree 4. However, some of these linear factors have exponents on them, right? So like this one right here has a 2. That means that x minus 2 is actually occurring twice. Okay, so this is a double root. This is a double root, right? We have another one being raised to the 2nd power, and this one is a triple root. So there's 3 of these linear factors. They're just being condensed using those exponents. Okay, so we actually have 1, 2, 3, 4, 5, 6, 7, 8 linear factors. So the degree of the polynomial is 8. Okay, leading coefficient, when we look for the leading coefficient in its factored form, we look in front of all of the parentheses here. That's where we can find the leading coefficient, so that is -7. So now they want to know the end behavior. No problem, so we look at the degree. It is even, and the leading coefficient is negative, so we have an even negative. And the way that I remember the even one, so I just think to a basic parabola, because we've seen those before, and a parabola either goes up, up, or down, down, depending on whether or not there's a negative in front, right? So this is even, so it's either going to go up, up, or down, down, but since there's a negative in front, this is going to go down on the left and down on the right. So it's a down, down polynomial. All right, so the next question is, what are the roots? And we've talked about this relationship quite extensively in the first 2 lessons so far. We can determine the roots by figuring out what values of x create zeros in these linear factors, right? So for this first one, since we have an x minus 2, one of the roots is going to be a positive 2. For this one, since it's an x plus 5, one of the roots is going to be -5. Okay, and the reason being it is pretty simple to find out. You can usually tell just by looking at it. But if you plugged a -5 in here, you would get -5 plus 5. It creates a 0. All right, that's how you know you've got the right number. Okay, so x plus 1, that's going to give us a root of -1, and then we have another x plus 1 here, so that's going to give us a root of -1. But we already had that, so we don't have to mark it again. Theoretically, actually not theoretically, if we wanted to here, we could combine these x plus 1s. This should be x plus 1 to the 5th power, but that's okay. Alright, so it wants to know, are any of these roots double or triple roots? And this one was really tricky because it gave us the same two factors here, 1 raised to the 2nd, 1 raised to the 3rd, which means these should have been combined to be an x to the 5th. So these are not double or triple roots. Okay, but this one is. The +2 is a double root. There we go. Okay, so pretty easy stuff there. There's not a whole lot of calculation to do in these types of problems. It's mostly just observation, right? And making sure that you understand what these vocabulary words are and knowing where to look for them, whether you're looking at a graph or standard form or factored form. All right, so you just have to be observant. All right, pay attention to things. So we're going to do the same thing, but this time we're going to do it from the graph. Right? So as I said before, we want to make sure that we can find the same types of pieces of information from the graph. So here we have a graph over here, and I'm noticing right away, like it's asking what are the roots, and we know that the roots correspond to the x-intercepts in the graph, right? So they also call these zeros. Zeros correspond to the x-intercepts. So if I'm looking at these locations here in my graph, like this location here at -1, that is an x-intercept, which means I'm going to have a root of -1, right? And then I come over here, this one is at +1, so we have another x-intercept. I'm going to say we have another root at +1. And then here we have another one. It almost looks like it doesn't touch, but it does. This is a bounce. We've talked about the bouncing behavior before, but it comes up here, it touches, and then it bounces back down. All right, so we have another root at +3. And also notice here at -1 that as we pass through that root, we get that flattening behavior. We call that inflection, and that indicates that -1 is a triple root. Okay, so -1 is a triple root, and the 3 is a double root. And that answers the second question right here. And we were able to tell that just based on how the polynomial passes through those x-intercepts. Okay, so let's think about that. We've got this next question: what is the degree of this polynomial? So if this is a triple root, that means that this root occurs 3 times, this one occurs twice, so that's 3 plus 2, that's 5, and then we have another one here that is 6 roots, and if we have 6 roots, that means the degree must be 6. The degree corresponds to the number of roots. It also corresponds to the number of linear factors. All right, so we know the degree. Now they want to know what is the end behavior, so we can go to the graph and we look at the ends, right? So as I go off to the left, right, so as I go off to the left side of this polynomial, is my polynomial going up or down? Well, here it is. This is the left side of the polynomial, and it is heading down, right? So I know the end behavior is down on the left, and then as I go off to the right, what direction is our polynomial going? Well, I'm looking here, here's the right, and it looks like this one is heading down. So we have a down, down end behavior, okay? And what that tells me is that the leading coefficient is negative. Okay, so we have an even degree with a negative, and that gives me more information to help me write the equation of our polynomial. So I'm going to say y equals, and I'm going to put a -1 out front because remember we figured out the leading coefficient was negative because of the end behavior, and I'm going to start writing my factored form for this polynomial. So we know one of our roots was at -1. That means we have to have a factor of x plus 1. Okay, so again, think about it. If I took this negative 1 and I put it in for x, right, we get negative 1 plus 1, which is 0. That's what we want. So that's how I know it's an opposite there, right? We get a plus 1 for the negative 1. And since this was a triple root because of this inflection, I have to raise this linear factor to the third power. Okay, so we have another root at x plus 1. Okay, so when I write this one, again, we're going to go x minus 1. So it's kind of like it's doing the opposite, but really we're just trying to create a situation where a 0 occurs. Right? So if I take this one and do 1 minus 1, I get 0. That's how I know I got the right number. There's no special behavior at this x-intercept, so it's just a regular linear factor, no power. Okay, so we got one more root here at 3. It's a positive 3, so I'm going to need an x minus 3. And because of the bouncing behavior, we're going to have a double root, which means I need to raise this to the second power. And that will complete our equation there. That's really all we needed. So we found the end behavior so we can determine the leading coefficient. We needed the roots so that we could write the factors, and we had to pay attention to the behavior at each of the x-intercepts to determine what exponents we needed on each of those linear factors. Alright guys, that's it for today's lesson. Make sure you give the practice problems a try and let me know if you have any questions in the Zoom chat. Have a great day.